Okay, so in today's class, we'll primarily do Kane-Milly model for quantum spin Hall effect. So, Halden model, in the previous class we discussed Halden model, which explains the quantum anomalous spin Hall insulator phase, which have non-trivial topological edge state where bulk is insulating, but edge due to the edge we have non-zero charge number, and there can be uh, I mean current conduction because of these edge state. And yeah, so those edge states are non-trivial, meaning charge number is zero, sorry, non-zero, in time reversal broken system. So Halden model was basically a time reversal broken system which have non-zero charge number. Now, in quantum spin Hall effect, we do not need to break the time reversal symmetry explicitly, and we'll see that how without breaking time reversal symmetry, we can have non-trivial edge state. Okay, so if any of you have any questions, then you can ask. Otherwise, I'll go to Ken-Milly model. Okay, so the Ken-Milly Hamiltonian, and this was discussed in one of the uh, PRL 2005 by Charles Kane and E.J. Mealy. So this is the paper. So if you write in second quantized notation, then the tide binding Hamiltonians look something like this. Okay, so this is the Hamiltonian, where this is the so this term is the conventional nearest neighbor hopping that we are considering in the conventional graphene case, which we have from A sublattice to B sublattice, let's say. So nearest nearest neighbor hopping, and this is the, and this second term is the most crucial, introduced by Kane and Mealy, which represents spin orbit interaction. And this spin orbit interaction acts on the next nearest neighbor, actually. Next nearest neighbor. And this is the conventional sublattice potential, where A atom and B atom will have some different on-site potential, which will break inversion symmetry. Or rather, we can also write staggered sublattice potential. staggered means in two sublattice, the sublattice potential is different. Okay, and this difference is created by xi I. Xi I is some coefficient, let's say. So if you are on the A sublattice, then xi I have some value, and in the B sublattice it will have different value. And the simplest thing that we usually take is that in A sublattice, if we consider V, and in B sublattice we usually consider minus V. So xi I is +1 for one sublattice and -1 for another sublattice. But this is particularly a choice, doesn't matter, because it will just shift the overall energy by some constant factor. Okay, and this phi ij is again what was introduced by Halden. So we will have kind of periodic or effectively zero magnetic field, but within a unit cell we will have some magnetic field, so that the phase because of those magnetic field uh, adds up to zero, right? That's what we studied in Haldane model, let's say. So so this was the Haldane model case where we had per unit cell the phase was theirs, but overally the magnetic field was zero. So these phase are I mean included by this e to the power I phi to the power minus I phi terms in the Haldane model. So Kane-Meyle did what they did is just the generalization of Haldane model, including the spin. Sz is the spin component along the z direction. So if we just compare this with the Haldane model, just for clarity, then so we had Haldane model, Haldane. So again T, conventional nearest neighbor hopping. So this Hamiltonian way I am writing in the second quantized notation, where Ci dagger creates an electron at the ith site and Cj dagger annihilates an electron at the jth site, plus let's say some hopping parameter. Let's see which we denoted. So T2, let's say. So T2 was the Haldane parameter. So I am writing T2, and then again next nearest neighbor hopping. So this double curly bracket means these are next nearest neighbor, whereas single bracket means nearest neighbor. Again, the phase due to magnetic field such that within a unit cell phase are arranged in such a way that total magnetic field vanishes, because we have not applied any external magnetic field, and that was the specialty of Haldane. Haldane introduced the idea of quantum Hall effect or quantized Hall effect without any explicit presence of magnetic field. And then again that staggered sublattice term, let's say. So note that this is Ci because these are sublattice terms. So this is only associated with the each. So let's say we have an A atom here and B atom somewhere here. So this term represents actually the potential at this place only. Okay, whereas these terms T represents the hopping between the nearest neighbor, and then somewhere, let's say here is A, another A type atom, then this is the next nearest neighbor is represented by T2. But this Ci dagger Ci means there is no J, that represents that we have some on-site potential which depends on which sublattice I am in. Okay. Okay, so if you compare these two equation, Hamiltonian of Kane-Meyle and Hamiltonian of Haldane, you'll see the only difference is this term basically, right? This term, and they are also looking almost very similar, unless this SZ term is included in the Kane-Meyle model. So the only difference is that. So what is essentially we can say that it is kind of a generalization of a Haldane model for the spin orbit coupling. I mean including the spin orbit coupling. Okay, SZ represents the spins. So So the essentially the HKM is simply two copies of H Halden. Two copies means here Sz equal to plus minus 1 for both the spins. Now this have a remarkable consequences in terms of in explaining quantum spin Hall effect and other things, and we can explicitly show that this Hamiltonian Kane-Melle Hamiltonian doesn't break uh, parity symmetry unless the sublattice potential is there. So these two terms doesn't break parity symmetry, whereas sublattice potential breaks it. And the so the point is ki this new term lambda issue term, so the term associated with lambda issue or the we call it Kane-Melle term doesn't break time reversal symmetry. So this also doesn't break actually parity symmetry. This can be easily proved. But one of the ways to understand why it doesn't break time reversal symmetry, one of the simplest way uh, drawing parallels between Halden model and Kane-Melle model is that this term actually breaks T, okay, in Halden model, breaks time reversal symmetry. And that's why we got non-trivial H state and non-zero Chern number, let's say. And as we have discussed in the previous class that spin also breaks time reversal symmetry. Sorry, spin also changes sign under time reversal symmetry. So Sz under time reversal symmetry will go to minus Sz. And the reason we explained that it is kind of an angular momentum, and angular momentum direction changes under time reversal symmetry. So this whole term without, so this whole term without time reversal, sorry, Sz operator or Sz term breaks time reversal symmetry, but then Sz also changes sign. So effectively the symmetry remains intact. The time reversal symmetry remains intact. Okay, so that is the essence. So this we can also understand from k-space form of this lambda isoterm. So this Hamiltonian I have written in the lattice basis, meaning they are kind of in the real space picture, so where ij terms are there, meaning at the ith place there is some creation of electrons, and then at jth place there is some annihilation of electrons. But if you write in the k space, this spin orbit coupling associated term will be, so this I am representing by dso, and z is representing just the sz, or I can write even sz, the function of k, which will be given by lambda so, and then again sz sine phi is that phase, phi ij it is coming from, and then sine k dot a1, and then sine k dot a2 plus sine k dot a3. Okay. And a1 a2 a3 are nearest neighbor vectors, a1 a2 a3. So actually this should have been next nearest neighbor vectors, right? So next nearest neighbor. Okay. So how can we see this term remains intact under let's say p symmetry or parity symmetry? because under p symmetries, so Hamiltonian, p is the parity symmetry or inversion operator, Hamiltonian as a function of k should go to minus h of minus k. Okay, so that's the kind of definition of p symmetry for an Hamiltonian in k space. So if you see this term, so okay, see this term is nothing but when you write this, let me use a different color. So this term is nothing but when you write this term in the k space. Okay, so uh, so if you see from DSO SZK, so lambda SO is just a coefficient, it has some constant value, and then SZ spin doesn't change under parity symmetry. So parity, under parity, SZ do not change any sign, so SZ remains intact. Again, this also can be understood uh, from the picture of angular momentum. And then sine phi is again some constant, but what really changes is that k, this k, a are the constant vectors which do not change because these are some specific direction, a is some constant nearest neighbor vectors, let's say. Now k changes sign under parity symmetry. Okay, so under parity symmetry, k and r, let's say r is the real space any vector and k is the vector in reciprocal space, both of them changes sign. This is minus r. So because of this, and there is a sign, so sine of minus theta is minus sine theta. So what really happens is that under parity, d so sz of k goes to minus, this minus is coming from the, let's say k will be minus k and sine will be then minus sine of k dot a, right? So so this will be, yeah, so this will be djszso of minus k. Okay, so what it essentially means is that if you do dso of sz of minus k, then you will get, uh, or rather we can also write equal to minus of dso sz of k. That's what it means. And since this is valid, so that means the Kahn-Miller term preserves time reversal symmetry, sorry, inversion symmetry. And as I already said, that is also preserves time reversal symmetry, which we can understand from the fact that Haldane model breaks time reversal symmetry, but we are adding extra spin component, and spin component also changes sign under time reversal symmetry. So effectively, they do not change. But nonetheless, this can also be kind of proved from the, from explicit time reversal operators. We need to take minus I sigma y k. K is the complex conjugation. So if we take the time reversal operator of this form and then take d so sz of k and then time reversal inverse operator, then we will see that it will be actually d so sz of minus k. So since this is valid, you can prove it, this is valid, then the Kahn-Miller term preserves time reversal symmetry. So we have a model which in general, in principle, breaks both the time reversal and inversion symmetry, but we will break inversion symmetry by introducing this sublattice term, okay, V. Even if you do not break, this doesn't really matter, okay, that I will show explicitly using some, I mean, some software called Quantum Lattice. Okay, so let's see, let's see a little bit more details about the, I mean, this Kenmele term or Kenmele Hamiltonian in the K space. So this is in the real space, what we see here. We'll see in the K space. That is more easier to understand, let's say. So in graphene we have, let's say graphene, we simply had 0 f of k, f of star of k and 0, let's say. And f of k was given by, let's say, t sum over I to the power I k dot delta I are the nearest neighbor hopping vector. Now this Hamiltonian is actually a spin degenerate Hamiltonian. So in reality, all the electrons can have both spin off and down. And in the conventional graphene Hamiltonian, since we didn't consider any spin orbit coupling, so for both the spin off and spin down electrons, the Hamiltonians are essentially same. So what really means is that if we also write in the spin basis, so this Hamiltonian is purely in orbital basis. So this is A orbital, sorry, A sublattice and B sublattice, again A, B. And for A sublattice, we are considering PZ orbital. This is also PZ orbitals, because remember that we had 1s, 2s, 1s2, 2s2, 2p4, and then after hybridization, what is happened is 1s2 remains 1s2, but 2sp2, so 2s orbital and px and py orbital kind of hybridizes to form a 2sp2, and then 2pz. This is kind of lone pair, I mean this remains as it is. So this is the uh, orbital characteristics of, let's say, graphene when they form, so carbon atoms when they form graphene in hexagonal structure, right? So so we had this pz. So for both the sublattice, pz orbital contributes, but then pz orbitals, when you break it, so why, so how do we feel those orbitals, right? So we had px, py and pz, px, py and pz, and as you see that we feel orbitals something like this, right? So this means in each orbital we can have spin up and spin down. So here when we derive graphene Hamiltonian from the tide bending perspective, we never mentioned spin, but in principle these Hamiltonians, graphene Hamiltonian, are actually given by Hg, let's say, will be given by H graphene, and then 0 0 H graphene, and these are in the spin basis, let's say. So let's say we are representing spin off, spin down, spin off, spin down. So if we further divide it or further explicitly write, so each graphene is nothing but again 0 f of k, f star of k, 0, and then this is 0. This single 0 means all components are 0 for this block diagonal position. Again this is also 0 0, and we'll have something like again fk, f star of k, 0, right? So uh, so what it really means, these two are the spin up basis, these two are the spin down basis. Now all are pz orbitals, and for graphene we had e of spin up, let's say, b of spin up, and a of spin down, and b of spin down, something like this. The complete basis set is like that. Because so graphene Hamiltonian was a sublattice pz orbital, and all are obviously pz orbitals, needless to say. So this is the kind of 4 by 4 Hamiltonian for graphene, considering both the spin up and spin down. But we consider, or we in for all practical purposes, spin orbit coupling in graphene is very less, so we consider only one block of it, and just the other block is just exactly same whenever we do not have any spin orbit coupling or it is extremely small. So it is needless to work with 4 by 4 Hamiltonian, because the features or the band structure and so on are essentially exactly same for both the spin up sector and spin down sector. Okay. Okay. Now let's write Hamiltonian in K space for the Kenmele term. So Km, and this is obviously will be in spin space. So we have some potential term, let's say, I mean sublattice potential plus minus d, or rather I can write just a second. So the simplest way to write will be, yeah, so we can write this as dz or dso, let's say, uh, sz of k, and then this previous h, sorry, f of k of graphene, and then f star of k and minus v. I am simply taking for a sublet is the on-site potential is v, and then for b sublet is it is minus v, and then minus plus bsz so of k. So this is so what this, so the upper sign corresponds to the spin up and the lower sign corresponds to the spin down. So this plus sign here, so the plus signs corresponds to the spin up and minus signs corresponds to the spin down. Okay, so this is definitely spin result, but I have not written explicitly in the 4 by 4 basis, but I have written, so since they are kind of block diagonal, so we can write this. Okay, okay, and so this is the Kahn-Miller Hamiltonian in the K space where d, f of k we already know, and ds so is given by this expression. So it was, so this expression basically, and it represents for both spin up and spin down. And another thing is that in time reversal symmetric system the energy are related by, for spin up at some k point is related to spin down minus k if there is time reversal symmetry. If there are any time reversal symmetry of the system. Now for a time reversal symmetry we already discussed at length quite a few times that we'll have Chern number to be 0, right? So Chern number, Chern number equal to 0 for time reversal symmetric system. So what is the topology and how this helps in having quantum spin Hall effect, or let's say any other thing, and why it is non-trivial or let's say important, right? So so what we can do to define topology in this case is that total Chern number is definitely 0 because there is time reversal symmetry, but we can define Chern number, spin resolved Chern number you can think of. Okay, so that need not be 0. Okay, so spin resolved Chern number. So Chern number for up spin and Chern number for down spin. This we can define, and this doesn't necessarily needs to be 0. Okay, C up and C down may not be 0, but when you add them to have the total Chern number in the system, so C up plus C down, it must be 0 because of time reversal symmetry. And it turns out that the Kahn-Mene model actually does this job of C up and C down not being 0 individually, but when you add them up they are 0. Okay, So we'll see, or we can already anticipate that there will be some kind of, there may be some kind of edge state which will be there, but in total there should be no char number. So each edge state should be kind of supplemented or complemented rather with another edge state with opposite spin, so that C up for up spin and C down for down spin are already zero, but meaning when we add them they are zero, but individually they may not be zero. So this already kind of gives an indication that there might be edge states which will look like uh, uh, so so if I have a sample like this, so these are, let's say, finite geometry samples, then we can have edge state something like this. This is one edge state and this is another edge state if this is of spin up and this is of spin down. And similarly, another edge, this will be exactly opposite. So this will be for spin up and this will be for, let's say, spin down. Okay, something like this. Okay. So now let's see that similar to what we have numerically shown for the Haldane model, that once you start or once you switch on the Haldane parameter, the system develops a non-trivial edge states, and in the zigzag finite geometry or zigzag graphing nanoribbon. So let's see that again what happens for Kane-Meillet model, let's say. So just give me a second. This is taking longer than expected, but let's see. Okay. Uh, okay. So I'll share my screen. Okay. So I hope you are able to see the screen. So yeah. So we'll work with 1D system, which is nanoribbons, because we are talking about edge state. We are not necessarily in the bulk where we have infinite lattice system in both x and y direction, but we are interested in 1D system. So again, this hopping terms is just the nearest neighbor hopping term, and we just need to look at Rasba, Kane-Meillet term and Haldane model. So just for continuity, let's switch on some Haldane parameter and choose honeycomb zigzag of the graphene, and this is the structure. Okay, and if you see those bands, let's see. Okay, so you see there are some non-trivial edge state. So the bulk is insulating in a sense that this is essentially an insulator type of behavior, but then there are two counter propagating states which crosses the zero energy. So doesn't matter where is your Fermi energy lies, even if it is in the kind of gap, these two edge state will conduct and give some non-trivial behavior. Okay. Now let's see what happens if you switch off the Haldane. Let's say now we are interested in the Kane-Meillet. So switch on some Kane-Meillet parameter and see what happens. Okay, I need to see bands actually. Then I need to also turn on the sublattice imbalance term which was there. Okay, yeah. You see, now instead of one edge state, now there are two counter propagating edge state. I mean, these are the two counter propagating, and these are another set of two. And these two actually corresponds to one is spin off. So if we focus on this counter propagating state, then one will be spin off and one will be spin down, and same for this case also. This will be one spin off and spin down. And this is a result of this Kane-Meillet term being finite. Okay, so this is what we can say, that if you look at one counter propagating I mean one edge of the sample, then these two edge state have up and down, so they kind of uh, gives zero, total Chern number is zero, and for this also this is zero because there is up and down. So this represents that total Chern number being zero, but I mean the spin resolved Chern number are finite, and they conduct the spin Hall effect, which is a spin polarized current. Okay, so this is the story of quantum spin Hall effect, and those spin currents are quantized in units of, again, E square by h when we talk about conductivities and so on. Okay, so yeah, so another spin orbit coupling can be, so this is Kane-Meillet type spin orbit coupling, which is intrinsic to the system of graphene. Although intrinsic spin orbit coupling in graphene is extremely small, it is kind of order of micro electron volt. Okay, and this has to be contrasted. When I say very small, this has to be contrasted with the band structure of graphene, which is of the order of EV, or let's say MEV if you are around the Dirac point. So the normal band structure or Dirac point uh, have MEV, I mean energy of the order of uh, milli electron volt, whereas the intrinsic spin orbit coupling, as in graphene, of course, have the order of micro electron volt. So it is already 10 to the power 3 times lesser than the intrinsic, uh, energy of the Dirac electrons in graphene. So it is very difficult to show in graphene, but nonetheless it gives a very clear idea that in time reversal symmetric system also we can have non-trivial, I mean edge state and non-trivial topology, but then you need to see not the charge response but the spin response, and talk about spin resolved Chern number and so on. Okay, okay. So let's move to, just stop sharing. Okay, so how do we define Chern number, or to characterize the these spin sectors? Is that we define Chern number, or let's say new, we define something different. This is defined by, let's say, spin up minus spin down by 2. So this is kind of course this is modulo 2. So this is a kind of spin resolved Chern number thing which characterizes the quantum spin Hall insulator phase. Okay. Okay. So another thing I just forgot to show you there in the quantum lattice picture is that if you remove the lambda SO or the Kn-Meillet term Km term and add Rasba SOC, which can be there in graphene when you make a graphene WC2 type heterostructure or any heterostructure with graphene where the material that you are using in contact with graphene is or having a strong spin orbit coupling, where Rasba SOC you can add, and this way you can add Rasba SOC to the Dirac electrons of the graphene of the form of, let's say, lambda r Rasba SOC and then sigma x sx minus sigma y s x, something like this. uh, if you add this term and remove the Kn-Meillet term, and if you see that are there any edge state or not, you'll see that although there is bulk band gap, but you will not see any edge state. So similar to the Halden model where we have seen that only adding sublattice potential will not give you edge state. Here also you will see that edge state are I mean states are connected something like this. They will not, there will not be some no states like this. Okay, so this will not be there if you only take Ras by term. So that means Kn-Meillet type intrinsic spin orbit coupling is crucial in for graphene to have a quantum spin Hall insulator phase, which is a non-trivial topological state, even though there is time reversal symmetry in the system. Okay. So that's the thing about uh, Kn-Meillet model, which is kind of extension of Halden model to explain quantum spin Hall insulator phase. Okay, we'll stop here, and this was supposed to be the last lecture. Uh, so since no doubt is there and no one came up, so I'll stop here.